Okay, in this video, we're going to talk a little bit about basic logic. We can't get anywhere without it. At least we can't if we're going to try and discuss the genetic code because it's pure logic. So I have a pretty simple approach. I think that there's two things in logic. There's true and false. And so we can, this is Boole invented this concept of a binary logic, and that's the basis of information theory and computers and everything. So I think we can pretty safely use it for what we're going to do here. I personally use set theory, or at least my version of set theory, to get through. This is what I use to think. This is what I use to do all my mathematics. This is how I program a computer. And to me, a set is simple. The simplest form of it is a Venn diagram, where you can just draw a circle and say everything in this circle is a certain thing. So we can see that if it's in the circle, then it's true. If it's out of the circle, it's false. In computer terms, this is not true. So this is true, this is not true, true and false. So it's pretty easy to create a set. All you have to do is come up with something to put in it. So I could say I'm going to make a set with all 5 of the perfect solids. Okay, now I just made that, and then I created a set by drawing a circle around. So if it's in this set, it's a perfect solid. If it's not in this set, it's not a perfect solid. For real things, I think more in terms of a bag. So a set is a bag that you can put something in, and you could say if it's in this bag, it's a perfect solid. If it's not in this bag, it's not a perfect solid. Now you can get clever and say I want to make a bag that has red perfect solids. And in this case, this is an octahedron. So this is a bag with all of the perfect solids that are red and have 8 sides. So this set, it's true that they're perfect, it's true that they're red, and it's true that it has 8 sides. So this is the way I think when I take notes in class. You make outlines. This is related to this. So you end up nesting things. Now when it comes to computer programming, we can use these kind of ideas. This is how I think in terms of writing a computer program. So information comes in sets. We have inputs and outputs. So for instance, our inputs are a set, our outputs are a set, and then we have code that changes our inputs to outputs. So the things that are here. So this is like a function. So we have inputs and the function outputs. So we have a set of instructions that go in here. And then we get from A the inputs to B. Well, this is how language works. So, if this is my brain in A, and this is your brain in B, then the set of all thoughts in my brain can be translated to your brain through a language, and the language is a set. Well, this is how we should think about any language. And in some cases, the language itself encompasses the inputs and outputs. That's the case in the genetic code. Now, when we write code, we do a particularly powerful thing is an if-then statement. So if this is true, then do this. This is the basis of logic, where we have this is the premise and this is the conclusion. Okay, another thing that we do um, is a for. We can do a for next loop. So the thing that goes through this set of instructions gets incremented and repeated. Okay, well, this requires a variable x before you can do that. So this is a form of pure logic. This looping. Now, when you have a function that calls itself, okay, that's called a recursion. Now, this is a very common thing everywhere. Recursion, loops, arguments, premises, conclusions. Now, science, which depends on logic and depends on these kinds of language things, is very susceptible to these recursive arguments. And what happens is they tend to describe something by invoking that thing. And so you've got a premise that's stronger or more important than the conclusion you're trying to derive. So you get this cyclical thing. Okay, this has a name. This is called a homunculus, which means a little man. This homunculus idea is everywhere. It's a logical fallacy where you get into this infinite regress. There's a joke, a guy comes up and he says, "Hey, I figured out how the world works. The Earth sits on the back of a giant turtle." And the other guy goes, "Well, that's amazing. What does the turtle sit down?" And he goes, "There's another turtle. So the Earth sits on a turtle, sits on a turtle." And the guy goes, "Well, that's just incredible." He goes, "What's at the bottom of it?" He goes, "That's just it. It's turtles all the way down." Well, that's a homunculus, and that's something that is a logical fallacy. You're taking a premise that's much stronger than your conclusion. And this is something that we see everywhere in science. I mean, it's embedded in everything. And when you see one that's really bad, then you know you've got a question of science that needs an answer. And that's what we see with the genetic code. I mean, it's like they take every logical fallacy they can find and use it, and they make every mistake. They just ignore math, science, logic, everything we know. And they create this paradigm, and it's so airtight that you can't even talk about it. So anyway, as we start to examine the paradigm that they've built and how they built it, we need to keep in mind that despite the fact that they're not using any logic, we need to understand what logic they're using, why it's incoherent, and we need to start applying logic as we begin to imagine how we're going to fix this paradigm.